come from control system and in the gate 2021. The complete next plot of the open loop transfer functions GSHS, right? GSHS has been given, and it has also been given that GSHS has 1 0 in the right half S plane. This GSHS functions has 1 0 at the right half S planes. The number of poles that the closed loop systems will have in the right half S plane. Here we need to pinpoint two concepts. One is the encirclement property, another one is the next stability criteria. Encirclement property will gives the number of poles of GSHS in right half S plane. Then next stability criteria will gives the number of poles of closed loop transfer functions in the right half S plane. So to begin with these questions, I will cover up some of the basics of the encirclement property. Let one complex function fs which has 2 0 and 2 pole, and also fs when s tends to 0 is finite or 0, that is rational transfer functions. Draw the S plane. Let's see the pole location like this. Sorry, this is the 0 locations and you have pole locations. Similarly, the FS plane, this is your real axis and this is your imaginary axis. If you encircle and enclose 1 0 in clockwise directions, in the FS plane you will enclose origin in clockwise directions according to the encirclement property. If you includes 1 poles and 1 0 in the encirclement, then you will not include or you will not encircle origin of FS plane at all. Next case, include only poles. Let's say you include 2 poles in clockwise encirclement. According to the encirclement property, you will encircle origin of FS plane in counterclockwise directions. Two times. That means you will encircle the origin of FS plane in counterclockwise directions twice. You can see that when you includes the poles, number of poles in one orientations, you encircle the origin of FS plane in opposite orientations. But when you include the 0, the orientation of including origin in the FS plane remains same. So the simple rule is Z equal to N plus P or N equal to Z minus P. What is N? Number of encirclement of origin in FS plane. Z, number of zeros included in the encirclement in S plane, and number of poles included in the encirclement in the S plane. You can now apply each point, you will find the same thing. For example, 1 0 no pole, that is Z0, sorry, Z1 P0, so N equal to 1, so N equal to 1 positive, that is same orientation. When here included one pole 1 0, z minus p is 0, so no encirclement of origin in the FS plane. Now interestingly, when you include the two poles in the S plane, you include the origin of FS plane twice in counterclockwise directions. Let's say n equal to z 0, p number of encirclement in the S plane is the 2, so n equal to minus 2. So this minus indicates the whatever the orientation originally in the S plane, the orientation of including the origin will be the different. Okay. Move to the questions. Here it has been given the Nyquist plot of the GSHS. But what is the Nyquist path in the S plane? Nyquist path in the S plane. So in the some books they starts from minus j infinity, goes through the 0, then go to the j infinity, then a infinity radius to cover whole of the right half S plane. Like the books I have studied that Ogata. In some books they define the Nyquist path, that is j infinity to 0, then minus j infinity, then to cover whole of the right half S plane within an infinity radius. So which one we will consider for the Nyquist path? To find the number of poles in the right half S plane of GSHS. So let us consider this path first. You can see the Nyquist path is the orientation in the clockwise directions. Here the orientation in the encirclement of origin also clockwise directions. That means your n equal to 2, because the orientation of Nyquist path and orientation of encirclement of origin is the same. So n equal to 2. So n equal to z minus p. So n is 2, z 1 0 in the right half S plane, 1 minus p. So number of poles in the right half S plane of GSHS is equal to p equal to how much? 1 minus 2, that is minus 1. Not possible. How can be a pole of a rational transfer function will be negative? I mean negative number of poles. Poles can be negative, but negative number of poles. Where 1 pole, 2 pole, no pole, but minus 1 pole. It's not possible. That means let us move to the automatic control system books. Kuo defines like this. It says that because this orientation is actual conventional orientation, because theta is also measured in the counterclockwise directions. So come to this type of this Nyquist path. Here the orientation of the Nyquist path in the S plane is the different from the orientation from the orientation of the encirclement of origin in the GSHS plane. That means n is equal to minus 2. So n equal to z minus p. So minus 2 equal to z minus p. Z is your 1 minus p. So p will be your 3. What is this p? That is number of poles of GSHS. Number of poles of GSHS in right half S plane. One part of the question is complete. We need to find number of poles of the closed loop transfer function in right half S plane. For that, we need to consider minus j0 point. And net number of encirclement, same, z is equal to n plus p. Here z is the number of poles of closed loop systems in right half S-plane. So z equal to n plus p. So z equal to n plus p. Oh, what is the n here? Net number of encirclement of minus 1 j0. So draw a straight line from the minus 1 j0 point, and you count the number of encirclement. We see that we have a 2 encirclement but opposite orientation. So net number of encirclement is 0. And number of poles of GSHS already we have found before, which is 3. So Z equal to 3. That is number of closed loop systems poles in right half S-plane is 3. That is answer is option D. Hope you have got it. Come to the next questions. Question number 33. The electric system shown in the figure converts input source current IST to output voltage V0t. The current ILT in the inductors and voltage VCT across the capacitors are taken as the state variables. Both assumed to be initially equally to 0, that is IL0 is 0 and VC0 equal to 0. The system is this question is a somewhat blending of control systems and network theory. Let us find out the state equations. So how we'll find the state equations? Writing the KCL KVL. For this case, you can see that this IS is equal to ILT and the current through the 1 ohm. So what is the current through the 1 ohm? First, what is the voltage through this 1 ohm? So this voltage, or you can say the VL, is equal to L DIL upon dt. So current IS by applying a KCL here is equal to IL. I'll just omit the T, okay? IL plus this VL upon 1 ohm. So VL is the L DIL upon dt upon 1, which implies L is also 1. So DIL upon dt is equal to minus IL plus IS. This is one equation. Now come to the second state variable. Again, we'll apply the KCL at this point B before we have applied at the point A. You can see that IS is equal to this current is equal to this current plus this current. That is, this current is your C dV upon dt, that is VC dVC upon dt, plus same, that is VC upon 1 ohm, that is this current is the C dVC upon dt, and this current is the this VC upon, because the voltage across this is the VC. So C is also 1. So dV upon dt is equal to minus VC plus IS. So you have IL derivative and V derivative. Here we have IL, so minus 1 0, and here minus VC, so 0 minus 1, and IL V plus in the both equation you have IS, so 1 IS is the state equation. Then we'll go for the output equations. Output is the V0. V0 is simply VC, that means 0 1 IL V. We have state equations. We need to find the controllability and observability. For testing the controllability, the determinant of B controllability B and AB matrix should not be 0 for state controllable. So we see that, or you can say the rank is 2 because 2 cross 2 matrix. So here B is your 1 1 and A multiply with the B, that is -1, and this is also -1. You can see that the determinant of this, or you can say the rank of this, is the 1. That means determinant is 0 because -1 and +1 0. That is, it is not state controllable. So sometimes it match with the options completely state controllable, false, completely state controllable, false, completely observable but not state controllable. Okay, not state controllable, though we got it. Let's move to the observable. Observable may state observable means C and CA matrix has the determinant should not be 0. So C is your 0 1 and CA C multiplied with the A. Okay. So first column gives you 0, then 0 1 when you multiply it with that is your -1. So determinant clearly seen 0. It is also not state observable. That means both the system is neither state controllable nor observable, because this is also determinant is 0. Here it was 0, that is for the controllable, and for observable the determinant is 0. That means rank of the 2 cross 2 matrix state controllable and observable matrix are not 2 because it's a 2 variable. So the system is neither state controllable nor observable. Let us move to the question number 48. A unit feedback system that use proportional integral controller is shown figure below. The stability of the overall system is controlled by the tuning of the PI control parameters Kp and Ki. Maximum value of Ki can be chosen so as to keep overall system stables, or in the worst case marginal stable, rounded up to 3 decimal place. Here the question is, by glancing it we can see that we'll use the Routh-Hurwitz criteria. So find the characteristic equations here. So we can see that overall GS, that is the multiplication of this is your KPS plus KI by S multiplied by this. So you know that characteristic equation is the 1 plus GS HS equal to 0. So 1 plus GS HS is 1. So GS HS, that is 1 plus KPS plus KI upon S into 2 into SQ plus 4 S square plus 5s plus 2 equal to 0. So characteristic equation will be simply s into s cube plus 4s square plus 6s plus 2 plus 2 kps plus 2 ki equal to 0. So s4 plus 4s cube plus 6x square plus 2s plus 2 kps plus 2 ki equal to 0. So arranging this s4 plus 4s cube plus 6x square plus 2 into kp plus 1 into s plus 2 ki equal to 0, right? So use the next Ruth Herwig criteria, that is your s4 sq s2 s1 s0. So 1, this is your 6, then 2 6, oh 6, no 5, this is your 5, not 6. This is your 5, then 2 ki, then here s cube, that is your 4, then 2 into kp plus 1. This one 4 into 5 minus this upon 4, 4 into 5 minus 1 into 2 kp plus 1 upon 4. So this will be the 5 minus 2 upon 4, that is half kp plus 1. I mean the second row. Okay. And this one will be the 4 into 2 ki. Here will be 0. So 1 into 0, 0 upon 4, that is your 2 ki. For this case, you will have, that is the first row s1, this into this minus 4 into 2 ki upon this. So you will have here 2 kp plus 1 minus 8 ki, right, upon 5 minus half kp plus 1. This, and this is your 2 ki. Simple. Here let's say second one case, that is 5 minus half kp plus 1 must be greater than 0, because first row must have all element positive, which means half kp plus 1 should be less than 5, that is kp plus half, right, kp plus 1 should be less than 10, so kp should be less than 9, right? But it has asked something, that ki. So ki, the overall system sensitivity pi, the maximum value of ki that can be chosen, so to keep the overall system. So maximum value, the keyword is your maximum value. That means we need to something differentiate, right? So here ki is involved here, right? So let us take this term. Okay, so 2 kp plus 1 minus 8 ki upon 5 minus half kp plus 1. So should be greater than 0. Whole term should be greater than 0. For marginal stability, we can assume that it is equal to 1 because this should be 0. So marginally, so at least you will have poles at the imaginary axis when the this term is one row has the 0, that is the first row has the 0, some 0 element. So one row that is your poles will be on the imaginary axis. So we can say that it's a marginally stability. Marginally stability means it still oscillates, but it don't grow. That is called the marginal. But you know that stable means it oscillates then settle, but marginal stable means it keep on oscillating at a fixed amplitude. Output keep on oscillating, but unstable means it oscillate with a growing amplitude. Ultimately it will be dangerous. So we have 2 into kp plus 1 into 5 minus half kp plus 1 minus 8 ki equal to 0, right? So what we'll do here, multiply 10 into kp plus 1 minus kp plus 1 square equal to 8 ki. So ki equal to 10 upon 8 kp plus 1 minus 1 upon 8 into kp plus 1 square. So we need to find the maximum value of ki, and you know that maxima, theory of maxima. So we normally take the d of dk with respect to kp. Why kp? Because ki is a function of kp. If we found a value of kp that would give the maximum values, value of kp should be obviously less than 9. Otherwise, say second row will be also 0. That will create another problem. Doublet at the imaginary axis. So as ki is a function of kp, we will find a value of kp that will give the maximum value for the ki. So dki upon kp, it is your 10 by 8. When you differentiate here, you will have minus 2 by 8 kp plus 1 into 1 equal to 0. When you equate to 0, you will find the optimum value of kp, that is 10 minus 2 kp plus 1 equal to 0. So kp plus 1 equal to 10 upon 2, that is 5. So kp equal to 4. Now question is, in the theory of maxima and minima, we have studied that we have to check whether it is a maximum or minimum value. But we need not to check here. Otherwise, you will take the second derivative on this thing. Obviously, second derivative is not a tough here. Okay. So if you check that, when you take the second derivative, it is coming negative. That means this value of kp is your maximum point. That is, it will give the maximum for ki. So now we are nearing the solutions. So ki is equal to 10 by 8 into 4 plus 1, that is 5, minus 5 by 8, that is 8 upon 8 upon this, that is some 5, right? That is 10 by 8 upon 4. Okay, then here square na, this is a 25. So keep your eyes and mind open, because this thing can get wrong after doing all the hard work, right? Because this is the numerical answer type questions, so you cannot guess from the like multiple choice question. You can at least guess from the options. So 8 upon 50 minus 25, that is 25 upon 8, which is 0.1. Then okay, you can use the calculator. Something will be 3.1212 something, another one, the 4 5 will come. So this is your result. Here concept, let us discuss the what concept we have used here. See, nowhere I have written the calculator, I have used nowhere I have used the calculator in these questions. So try to do the questions as far as possible without using the calculators, like small multiplications, division, additions. So make sure that you practice a lot for appearing the gate. Here the question is, at the first glance you can see that is the application of arithmetic criteria, but here two variables are involved, and when you find that the one variable already kp which is less than 9, but the question is not related to the kp, that is the whether k, they have a beautiful design to give the answer the ki, and the keyword to highlighted what is the maximum, another one is the worst case marginal stable. Worst case you can take the equal to 0, that is at the first column you can safely assume that one element missing, that means it gives a poles in the j omega axis. So with this, the maximum, that means mostly if the maximum minimum is there, then you will find the differentiation of the that value involving the another functions. Okay, hope you have understood. Still if you have a doubt, you can comment in the comment sections.